Hello, this is Ben Engber. I'm the CEO and founder of a company called Thumbtack Technology, which specializes in custom software solutions that are highly scalable and fault-tolerant. And I'm here to talk to you today about how to evaluate NoSQL databases, especially along the lines of how we view the NoSQL marketplace is convergent. We're doing this on behalf of Aerospike, who is a longtime partner of ours, and focusing in particular about the set of use cases focused around where key value storage is most important. As you see, as I go through this presentation, we feel that this is actually the most important use case for much of NoSQL. And the talk itself is going to go into some depth as to why we believe this is to be the case. It's going to be a fairly technical conversation. I will ask that we've had some audio issues in the past, so if you are having some difficulty hearing me or want to provide some feedback on how to clarify some of the discussion, please use the question submission function, and I will take a look and do my best to revise accordingly. I can't hear what you say, so that's the best way to reach out to me. To begin with, let me just talk a little bit about what Thumbtack Technology is, who we are, who I am, and what we do. In essence, we are a software consulting company. We have a specific focus on building scalable systems. So our typical client is a client who has come to us and is either looking to build something more robust than your typical web application, or has built a web application that is starting to collapse under load and so forth. And so we do a lot of work around high performance websites and highly scalable websites, and that has led to a lot of work in the media industry and advertising industries and so forth. Like anyone who's been doing a lot of scalable development, we have a long background in NoSQL in general. The typical data problem is what to do when your data grows big enough so that you can't easily access it in a single data store. It's not a new problem. People have been dealing with it for a long time by doing manual sharding and other sorts of things that prevent them from accessing the database in a traditional SQL way. What has changed recently is a couple things. One thing is that a lot more kinds of database, a lot more kinds of applications are generating a lot more data. Certainly social applications have generated just a ton of data based on the relationships between people and so forth. And much of Web 2.0 just involves a lot of transactions and sorts of disk space to be able to handle it, which has led to a whole lot of more uses of data and more ability to collect a lot of data. The other thing that's changed is the industry has developed around this reality. A lot of NoSQL databases have emerged in the market that allow people to handle this out of the box. So what we used to have to do in sort of a kludgy way and build distributed storage systems that were a pain to maintain and didn't work that great is now becoming standard. And there's a lot of products out there that automate the distribution of data and do a lot of this hard stuff for you, allowing you to focus on the application itself. Because of this, we've been really eager followers of the NoSQL movement since its inception. We have a lot of partners and so forth, and this is very central to how we do a lot of our business and a lot of the problems we solve. We have an engineering team of about 50 people, and sort of central to this, at any given point in time, we're doing just ongoing research, sometimes on behalf of a partner and sometimes just on our own, publishing papers, blogging about it, but focusing very heavily on this space. A major part of what we do involves helping people choose the right NoSQL solutions, helping them ask the right questions, and helping them guide them through the implementation of how to do it. And what I hope to gain out of this presentation is to give everyone here a jump start on what are important things to consider when choosing a NoSQL database, and also what are some of the things that are probably not all that important. And this isn't that easy to tell just from looking at their websites and so forth. So as I go along, sort of focus on where sort of the wrong way to go down is and the right questions to ask as we get there. So the way NoSQL databases are traditionally grouped is into these sort of three categories. And maybe I'll qualify that to say it's sort of into these three categories plus graph databases, which are almost an entirely different beast. But essentially they're grouped as key value stores, document stores, and then in Cassandra's case, as a column family. And we feel that, this is sort of correct in the technical sense, but it actually doesn't tell you that much. And it doesn't tell you that much for the reason that these databases are all moving targets. So, for instance, prior to December, Couchbase was absolutely a key value store. That's all it did. And then in December, they suddenly added secondary index support, and now they're a document database. Aerospike, with its 3.0 release, is adding secondary index support, and I actually don't know what they're now calling themselves, but effectively, it's just another document. If you have content that's indexed in multiple ways and you want to pull it by its key, conceptually you're accessing a document. I would also argue the same thing is true of Cassandra. If at a certain level you're dumping data into buckets and then you can query it by different fields within that data, what does that really mean other than grabbing a document? Sure, there are different feature sets, but ultimately the model of programming is fairly similar regardless of what you want to do. To go into a little more detail, I've actually pulled two feature set lists, annotated feature set lists, or I should say abridged feature sets, off the websites of just Mongo and Cassandra, and I chose these two just sort of arbitrarily. If you look at Mongo, you see they advertise things such as flexibility, ease of use, secondary index, dynamic queries, lots of features around building easy-to-use query functionality. If you look at Cassandra, you'll see things like multiple data center, tunable data consistency, basic transaction support, as well as some stuff about flexible schemas and so forth. And I have nothing against this list of features. I think this list of features is accurate in both cases. The problem is it's not very easy to compare directly because, both of these things do offer dynamic schemas, and that adds some flexibility, and both of these things do provide a scalability model with built-in sharding and so forth. Both of these things allow you to tune consistency. But looking at these feature sets, it doesn't really give you any real way to evaluate when to choose one against the other than the fact that they seem to kind of be emphasizing different things within the same scope. So taking a step back, how do you go about trying to make a decision of which database to choose? Well, I can't speak for everyone, but I can certainly tell you what our clients tell us when they come to us. The first thing we hear from clients when they come to us asking about NoSQL, more than anything else, probably by far, is because I've heard of it. Clients know that this is an emerging technology. They know that all kinds of major players have developed non-traditional databases or are using non-traditional databases to solve different kinds of needs. And they hear about huge performance numbers, and they think, great, I want a piece of that. As you can probably imagine, this is headed for trouble for the very simple reason that relational databases were created for a reason, they've grown in popularity for a reason, and they're very well understood. And so if you take a technology that's very well understood and has a nice interface to it that's called SQL and everybody understands it, and you simply remove SQL from it, all you've done is make your life really, really hard. So the first thing you need to come up with is a clear-cut use case. The second use case that people come to us about is they want rapid application development. And that schemaless storage sounds very appealing because they know how painful it is to deal with DBAs, and they know how painful it is to do data modeling and then suddenly discover they modeled it wrong and remodel their application. And that's actually a really great reason You need to be a little careful about it, though, because even with schema storage, the decisions you make affect you deeply down the line. In any of these databases, they will give you courses and advice on how to construct the proper way to store your data. But the advantage of rapid application development is very real, and it's something that we have leveraged ourselves very successfully with some of these databases on the market. The fact that you're here at an Aerospike talk, however, probably means that that's not your main concern. Where Aerospike really shines, and where some of the other databases really shine, is in these last 3 bullets. Supporting a really enormous transaction volume, distributing your data tier transparently and without difficulty. And what I put simpler administration here. What I mean by that is how to handle the sort of maintenance operation when nodes go up and down. These systems all handle this for you, with varying success, in a much simpler way than was possible in the past. And I circle them all here because all these things are really saying the same things. All these things apply to key value storage. If you take a key and you have some data associated with the key and you want it distributed across a cluster, replicated, and maintained in a way that it's there reliably, even in the event of maintenance operations, that's probably your main concern. And so the feature sets around this are going to be of secondary importance. And so I'm going to be looking at these in some real detail. Okay. So before I jump into that detail, I'm going to just discuss, again, we discussed, the questions people are asking. I'll remind you again to ask this question. Why do I really need this? If you've got some data, and it's a lot of data, and you're concerned that your data is going to double in size within the next year to year and a half, you probably don't really have a problem, because Moore's law is telling you that by the time this happens, your hardware, there's probably hardware in the market that can survive it. And again, don't be too hasty to leave your RDBMS behind, because they are really good at doing an awful lot of things, and you're going to lose a lot of functionality once you take that plunge. That being said, if you're growing faster than that 18 months and you really see your data exploding, or alternatively, if you're looking to add sort of graph or social capabilities into your application, you might be opening the floodgate to a ton of data that you never really had access to before. Once you get there, that's when we should really be focusing on how to attack the problem from a key value storage perspective. Specifically, we're going to be looking at how these tools achieve scale, and then the trade-offs in terms of durability, consistency, and failover that will occur once the decision is made. So we're agreed for the purposes of the rest of this talk that we're really going to be focusing on the scaling aspects of key value storage. First thing I want to bring up are sort of the wrong ways to start asking the question about it. One thing that comes up a lot with sort of our more educated customers is they've gone to some talks and seen some writings online, and the first thing they say, well, all right, how does this fit within the CAP theorem? The CAP theorem, for those in the talk who are not aware, says basically that you can choose 2 out of 3 of the following attributes. You can have your data completely consistent, you can have your system up all the time, or you can distribute it across a network. This isn't a particularly interesting trade-off in reality, because we've already discussed that we're interested in distributing our data across a cluster. So partition tolerance is a given of what we need. And the trade-off between consistency and availability isn't really a trade-off, because virtually every application has some needs in both of these categories, depending on what the question is. And more to the point, each of these databases doesn't really live just in one, I was going to say quadrant, but just in one area here. Each of them has some aspects of consistency and some aspects of availability, depending on different use cases, and often changing on a query-to-query basis. Consistency and availability itself is probably also a little bit vague as to what it means, because it turns the CAP theorem into an academic construct, and in fact you have much more specific business requirements of what data needs to be available at what time. And the last point is, as soon as you want to take that jump to supporting your application across multiple data centers, that whole consistency argument becomes kind of moot, because you get bounded by the very real physical limitation of the speed of light. There's only a certain amount, no matter how fast the rest of the system is, it takes time to get information, the data back and forth from one data center to another, so you almost certainly need to relax consistency for those types of events. The second kind of question that it's not unreasonable but can get you into trouble is what kind of exotic query support database can do. Each of these databases do advertise different kinds of features and indexes and so forth. But remember that at the core, the reason why you're choosing a cluster, a key value store, is the fact that it distributes things across multiple nodes for you automatically. This is a beautiful, beautiful thing when you're querying data by the primary key. The system will automatically determine which node to route you to and get you your data, and ensure that the data is up to date in a consistent way according to the needs of your application and how you've configured it. When you add secondary index support, there's only one thing your system can reasonably do. If you're querying for something that's not your primary key, your system, the storage system, is going to need to look up all the records which have that secondary key set to a value and figure out where they are, which in general is going to be on every machine, or more specifically, at least one machine holding every shard, depending on the number of replicas in your system. So there's nothing wrong with that, and in fact, prior to adding secondary index support for many of these products, people did this sort of thing all the time. They knew where the data was going to be. They denormalized it, so they'd look up, they'd essentially roll their own indexes. They'd store the list of where documents were based on secondary key and created another collection for that, and simply did a lot of primary key lookups. Given that these systems can handle huge numbers of primary key lookups, that's not a problem. But there's a gotcha here as well, that as the systems offer more and more exotic support, it's possible to fall into the trap of using your cluster as a traditional database, attempting to do ad hoc queries against it. And in this case, what you do is you end up building this great database that's optimized for scale, misusing it, and shooting yourself in the foot. So it doesn't take away your need to design your application carefully. So going back to the main question of what we're doing key value storage. Well, we agreed it was scale. And within this scale, we mentioned a bit before the consistency availability spectrum. I think from a business perspective, it's much easier to think of this in terms of a reliability and speed spectrum. At the fastest side of it, what you end up with is a cache. A cache is essentially just a key value store without anything else, and that's very useful. There's, along the spectrum, you can have things like persistent cache all the way down to a disk-back database. As I mentioned before, each of these databases has multiple settings and can sort of live in multiple places along this spectrum. And what I'm going to do is I'm going to sort of walk through in detail how these databases achieve this, because I think it's easier to understand how these databases work. It's easier to answer the question of where on that spectrum you want to fall if you understand a little bit more what's going on under the covers. In the examples I'm going to show, this consists of a cluster with 6 nodes. I describe them in 6 virtual shards. This doesn't really mean anything other than sort of where random pieces of data happen to live. It's useful for illustration. And a replication factor of 3, meaning that each piece of data is stored and then copied to 2 other nodes. If we look at a system like MongoDB, and not just like MongoDB, This is just standard master-slave replication, and it's actually exactly how replication would look if you took MySQL and sharded it into a couple of nodes, a couple of shards. This is what it would look like. In the pictures here, we've created two virtual shards, virtual shard A and virtual shard B, each of which contains a subset of the data. If you look on top, you'll see how a client will typically access this in the fastest possible way. You'll have a single client who will hit the master node for that shard for both read and write operations. This guarantees that every piece of data it gets is consistent because it's always hitting the same node. However, it doesn't return, it returns immediately after it writes the data to that single node, which means that you can get a successful write, and if that node then goes down, that write has subsequently been lost. If you want to get a higher level of reliability in place, you have the option of waiting until that data has been copied to at least one slave. That will give you the advantage of higher performance, higher reliability at the expense of some performance. If you look kind of something like Couchbase handles the same situation, it's very similar. The difference here is that instead of each node being focused on either being a master or slave, every node is a master for some subset of the data and a slave for other sets of data. In each case here, there's still 3 copies of the data, but each shard has one master. The way it does fast and reliable storage is exactly the same, however. It will always hit the master node, and the choice is simply to wait till it has been replicated to other nodes. When we get to a system like Cassandra or React or anything really based on the Dynamo paper, the situation starts to get a lot more complicated. If we're talking in our fast scenario, the main difference is that the data itself does not have any master nodes. Any single node that has a copy of a shard can function as a master for the shard. So if you look at the lower left part of this diagram, you'll see 3 clients, each of which are attempting to do an operation to some data that lives on shard A, on virtual shard A. In each of these cases, the write is made and the result is returned immediately, but the write takes time before it is replicated to the other nodes. This means that client 2, for example, might make a write to the node, get a success, know that the write has been written, and client 1 could come in after that and still get an earlier copy because the data has not been replicated. In fact, client 2 could. The way Cassandra wants to achieve greater consistency is by tweaking the number of objects, a number of nodes that are hit on any given read or write. So if you look at client 4, and the black lines, you see it takes the approach of not accepting the write until all the nodes have been written. If all the clients behave with these same semantics, where every time they write to every node, but they just read one when they read, the read is guaranteed to give you a copy of the latest data. The converse can also work. For example, if every client always writes to a single node and the system returns as soon as that write is complete, but every time it makes a read, it reads every node, all it needs to do is take the most recent read to get a consistent copy of the data. Client 6 shows sort of a compromise approach between the two. If you write 2 and you read 2, of the 2 that you've read, the more recent one is the more consistent one. This is how these systems achieve consistency, but there's something to understand here beyond just the fact that we have a trade-off between availability and consistency here. And the way to think about this is to think about what really happens when we're taking for example, how client 4 seems to function. If we're waiting for data to be written to all 3 replicas, what's going to happen is it will hit them at various points in time. So if it writes a new value to somewhere on shard D, to 4 and then 3 and then 2, what's going on with other clients as they're hitting this node? Well, the client might be requesting it multiple times. It might get an old copy, a new copy, an old copy, and a new copy, and not until the write completes for client 4 does the system guarantee that the transaction is complete. So this quote in the upper left here, I took from the DataStax documentation. It says, in distributed systems like Cassandra, consistency usually means that once a writer has written, all readers will see that write. Think about what that means. That is a weaker definition of consistency than we are used to. It certainly means that while writes are in progress, the situation is a little bit indeterminate. It doesn't mean anything like what we're used to when we say ACID transaction semantics. To do that, we should look to the Aerospike-like databases. The Aerospike and similar databases, maybe like FoundationDB or so forth, use the Paxos protocol to write data to all nodes simultaneously. So Aerospike also has a non-consistent mode, the fire and forget mode. That functions exactly like Cassandra. But when trying to write consistent transactions, it will provide true ACID semantics because the transaction will not commit to the nodes until it commits to all three. All right, I'm going to take a brief pause here because I just covered a lot of complexity in a short amount of time. So if you have any questions, please submit them. All right, let me just summarize some of what we went over. On this chart, we have 4 databases we've done a lot of work on. Aerospike, Cassandra, Couchbase, and MongoDB. And we've created 7 scenarios here. We leave out Couchbase for the reliable scenario because it's not really Couchbase's main use case, and frankly, we don't have really great data for it. The thing I circled here sort of points out that among the things we just talked about here, aside from the difference in what consistency actually means, we sort of created 3 categories of database. We created the pure eventual consistent model, which is Aerospike, Cassandra in eventual mode. Couchbase and MongoDB, as I pointed out, was always consistent, but in the event of a failure, they lose data. And then the purely reliable mode gives you reliability in the face of node failures. And the amount, I say consistency on node failure here, but of course that itself is tunable. You have to decide the amount of consistency you want versus the likelihood of losing multiple nodes at a time. I would be remiss if I didn't include this graph in any Aerospike presentation. These results are the results of a test we did for on behalf of Aerospike. They're very interested in seeing how their system worked on SSD compared to other major competitors in the marketplace. And what I want to focus on here is not the raw numbers so much, because I think Aerospike has probably presented that quite a bit, but the different scenarios here. The graph on the right represents essentially what a database running in a persistent cache mode. This is a database geared for the maximal performance, keeping the data in RAM and backing it to disk when practical. The scenario on the left is using the SSD as the primary storage and making sure that no writes that nothing gets returned until all the nodes have been written. What you can see is essentially very dramatic differences. For the RAM cache, both Aerospike and Couchbase can perform an enormous number of transactions per second. On the left, this is, of course, one of Aerospike's big selling points, is they're able to do this in a reliable mode at really high volumes. One thing I should point out is you'll see sort of the stragglers of MongoDB and Cassandra at the bottom. Those numbers are absolutely true. What I want to say about it is that some of these things focus, what this test does not measure is some of the rapid application development in the case of Mongo. And in the case of Cassandra, there's a lot of focus around that eventually consistent behavior, even across data centers, that can change the picture somewhat. But this is the kind of difference you can expect depending on what you're trying to make your use case be. The next thing I want to look at in terms of how these things actually perform in the wild is the sort of follow-up research we did, which sort of reflects how the databases behave in the face of node failures. So before I just delve into a bit about what's going on, I just want to sort of show this picture that we sketched up on what you might expect to happen when you have a cluster dealing with node failures. Between A and B on this document, first of all, I should say that the x-axis is sort of database behavior over time, and the y-axis is the throughput of the entire system. What we'd expect any clustered system to do is to work at a certain capacity when at full capacity and all the nodes are running. In the event of a node failure, we'd expect some kind of interruption followed by a gradual return to capacity, and the same thing to happen when having a node rejoin the cluster. In a perfect world, these times would be close to zero because the system is so smart it's able to recover from anything. So the question is to look at how this behavior actually looks under different scenarios. In this case, we're going to be focusing exclusively on Aerospike because I think the graphs really speak for themselves on what's going on. The first thing I'd like to show you is what happens when you take Aerospike. This is a 4-node cluster over here. It's operating in RAM mode with a subsequent write to disk. And it's running at absolute maximum capacity. We're just blowing it apart as hard as we can throughout all the time. The graph on top represents, excuse me while I've lost my screen for a second. Okay, the graph on top represents the transactions per second going through the system, and the graph on the bottom represents the latency in milliseconds of the average request at that period of time. What you can see in the 4-node cluster is once you take a node down, the cluster suddenly loses about 25% of its capacity. It's not a very interesting finding. You'll see that the system survives quite well, other than an extremely brief outage. It does repair as planned, but the system can't serve as many records as it can when at full capacity. It's not a very interesting finding, just sort of a baseline to look at some of the other ones. If you look at this next graph, you'll see that this is the case when we're operating at 75% of capacity. I think this is a pretty interesting test to run because, in theory, when at full capacity, we're only maxing out 3 of the nodes. So 3 of the nodes should be able to handle this, but no more. And you'll see that when running in RAM mode, it pretty much works just fine. There's a slight interruption, but the system continues to serve everything at sub-millisecond latencies. Now, once we move to a reliable disk-backed node, the situation becomes a lot more interesting. This is the exact same test, but instead of running as a RAM cache, we're making sure that writes go to all disks, to all nodes, in this case just 2 nodes because the replication factor is 2, and get written to disk. And what you'll see here is that once the node goes down, you'll see a little bit of chaos in the throughput and a little bit of extra latency because suddenly there's only 1 copy of data on some of these nodes, and that data needs to be pushed around to keep the system functional. But more interestingly, when the node rejoins the cluster, there's some major work that has to be done. I say major work has to be done because while that node was down, we're still talking about 150,000 writes per second. So 150,000 writes per second over downtime of about 10 minutes here is tens of millions of records. It's not clear exactly how many because it's not necessarily writing new ones every time, but tens of millions of records need to be migrated to this new node when it's coming up. So you'll see a brief period of lag as the replication comes into effect, and then a long tail of replication delays. Each of the databases we looked at handles this, somewhat differently. If you want to look at our report, we have a lot more graphs like this. These are also tuned over time, but in terms of capacity planning, this is a really useful thing to measure. So our time is rapidly, coming to a close, but I just want to highlight the main points here. When choosing a NoSQL system, first thing you have off the bat is trying to choose what your main goal is. Are you trying to solve graph problems really easily? Are you trying to perform rapid application development, or is it raw scale? Raw scale can also include graph problems, and different types of graph problems have, different things you might want to do within it. But if your main concern is scale, and that's a pretty broad class of problems where your main concern should be scale, the first thing you should do before thinking about any of the follow-up features is to think about what you want to do in this key value domain. That means specifically to focus first on which parts of your business need to have the fastest possible response, which parts need the most intense reliability, and for which situations this occur, both within your data center and across data centers. It's important that you understand how these databases achieve consistency and achieve durability, because consistency means different things for the different types of databases, and the durability differs depending on the types of outages you have, whether it's a full disk outage or just a temporary node outage and so forth. Once you have all these sort of slots in place, you should be designing your application around leveraging this core key value feature set. With those main design decisions in place, you can then look at all the additional features as kind of gravy to build on top of that. That's really the right way to look at it, because those secondary features, secondary indexes and features built on top of that are going to continue to evolve. And these databases are going to look more and more like each other as they keep adding these kinds of features on top. So if I had to summarize the result in one sentence, it's understand sort of the core storage properties first, and then layer everything else on top of that. That's the gist of my talk. Once again, my name is Ben Engber. The company is Thumbtack Technology. We specialize in NoSQL implementations as well as other types of scalability challenges. If you'd like to learn a little bit more detail about where some of these results came from, I encourage you to follow this URL where you can download some rather lengthy white papers that describe our methodologies for some of these tests in detail, or check out our blogs. And right now, I'd like to just open the floor for any questions that you might have about any of the material I just covered. All right, I'm not seeing any questions right now. I'm going to wait a few more minutes. Please feel free to chime in if you have any questions. I'm happy to go back to cover some of these slides in more detail. If not, hope you enjoyed the chat. All right, questions coming in. The question is, do you think Aerospike is a good data store for session data? The answer is certainly yes. One question you should ask right off the bat is how reliable do you need your session data to be? Very often, it's okay to lose some of this data in terms of an outage, but if you're distributing across multiple frontline machines, we're talking about numbers for reading a session. We're talking about numbers we've seen with just 4 machines of about 900,000 reads per second. That's an awful lot of traffic, and latency on those kinds of numbers are 1 millisecond. So the answer is definitely an unequivocal yes for that session data. Another question coming in is, are there more benchmarks in the pipeline? There are absolutely some more benchmarks in the pipeline. The benchmarks take actually quite a lot of time to do. It's very easy to measure this data, it's hard to measure it in sort of a fair way because there are so many dimensions in play, and the fact that these databases all work in pretty different ways. It takes a lot of sort of trial and error and a lot of work to try and make them comparable. In addition to the benchmarks, we're also doing a couple of, trying to think of the right way to phrase it, sort of proof of concept applications, taking a bunch of databases and determining, just showcasing some kinds of applications that you'd write with them, how you begin to write it. We expect those to be done in the next few months. Another question coming in, what's the trade-off? Something has to give. Is it the cost? Well, I'm having a little trouble trying to understand exactly. There are, of course, trade-offs here to begin with. If the question is, what's the trade-off between, why does Aerospike look so great on SSD? It was because the system itself, that was one of the main design considerations of it. And I do need to point out, for fairness' sake, that the study about SSD performance was done on behalf of Aerospike, so it is one of the things they look best at. The results were completely independent, but certainly they knew they were going to shine there when they asked us to do it. And yes, Aerospike is a commercial product, so there is a trade-off in terms of price. If you look at the trade-off of, sort of a technical trade-off, something like when running in fire and forget mode in RAM, things like Aerospike and Couchbase get enormous numbers. They get truly enormous numbers by serving a ton of requests very quickly through RAM and then saving to disk. And that's because they're effectively emulating our cache. That's not what that's not what, say, Cassandra and MongoDB are doing. So you're right. It's not. There is a trade-off there, in that MongoDB and Couchbase are doing all this sort of stuff under the hood and consistency stuff and so forth. It's not totally fair to compare them against the cache. In terms of the trade-off between NoSQL key value stores and relational databases, the trade-off is very, very clear. You can't join. As soon as the relational databases allow you to join anything against anything and run ad hoc queries, you completely lose that ability when trying to run a NoSQL distributed key value store. And that is probably the single biggest trade-off to make for people considering a movement in there. A follow-up, what kind of open source projects would you like to see created around Aerospike? I'm going to have to get back to you on that. We're actually sort of debating some of these things ourselves. We're thinking about providing some of this ourselves, and I've been going back and forth with some ideas. But again, if you guys have some specific ideas of what you'd like to see around there, I'd be very interested, because that would be great for our research team. I mentioned we have ongoing research for any of these that provides us, both expertise and training for our guys. So if you do have some ideas, we'd be very interested to know and happy to consider it, to talk to you. So my contact information is there. Please reach out. Okay, I'm going to wait about 1 more minute in case any follow-up questions come in. Okay, that looks like it's about all. Thank you very much for listening. Please do reach out if you have any further questions, and please, feel free to look at any of the more detailed studies where we go into our methodology and some other information in great depth and discuss some other databases more. If not, I look forward to next time. Thank you again.